Astronomers have now been working with James Webb for several years, and I'm sure you remember that sort of early flurry of we found the most distant galaxy and maybe our understanding of the cosmos is incorrect. Well, settle down, everyone. Science is progressing, and what was originally considered to be overturning theories, everything is working out quite nicely, and astronomers have learned a tremendous amount about the early universe. And yet there have been a lot of really wonderful mysteries that have shown up as well, that we're seeing highly evolved galaxies, spiral galaxies seen within the first few billion years of the history of the universe, that we are seeing this weird mystery, these little red dots, as well as supermassive black holes with enormous mass, again, early on in the cosmos. My guest today is Dr. Andreas Feist. He's an associate scientist at IPAC at Caltech, and he and some collaborators wrote a recent paper analyzing some of these very massive galaxies seen early on in the universe. And I brought Andreas on just as someone who is dealing with cutting edge work with James Webb to sort of update us together on where we stand. What are the big mysteries that are unfolding? What was, you might have heard, theories have been overturned? Maybe not so much. Things, the lambda CDM model of the universe is holding strong. And so if you want to hear, like, as of January 2026, what is the current thinking as it relates to James Webb and the early universe, and what are we finding? I think you'll really enjoy this conversation with Dr. Andreas Feist. Andreas, we have had access to James Webb now for years. And what has it been like as a cosmologist thinking about what you knew before we had access to James Webb, and now you're seeing all of this data come in? How has this changed your perspective of the universe?
Yeah, that changed it quite a lot, right? So we had, before JWST, we had models, theoretical models, simulations. So we kind of think, we should find those very high redshift, so galaxies in the very early universe, for example, right? So we had hints from the theoretical works, right? But we never really observed anything like that. And so obviously JWST was able to confirm some of those expectations, right? But then there were also a lot of things that we didn't expect at all, and that we could find with JWST the first time. And then it's kind of the reverse process. So those discoveries then again feed back into our models, and we can adjust our models to try to explain those observations.
So, you gave sort of two examples here. So I'd love to know, what is the stuff that had been theoretically modeled and it looks like the models were really good? Like James Webb is confirming what we had anticipated.
Yeah. So one big thing that JWST was designed for, right, was to find the first galaxies. And so we knew that they're existing about, redshift 14, 15, 16, 20, which doesn't tell you much, right? But it's basically, about 200 million years after the Big Bang. That's about the time scale. So we knew that those things probably exist, those galaxies. And so these are pretty much, as soon as JWST was operating, we were able to find those sources so far back in time.
Right. But I remember there was sort of this race. There was a whole bunch of papers came out saying, we found the farthest galaxy. No, we found the farthest galaxy. And we saw some pretty extreme versions from redshift 13 all the way out potentially to like 16, 18, 20, as you said. But now the more detailed spectroscopy work has come through, and we have a more sort of some specific numbers, right? It's been dialed in a little bit.
Exactly. Yeah. So this race that you're saying, it's very interesting because there are two different ways that you can measure the distance, right? You can do it photometric, which means you get a kind of a rough distance, plus minus something, but it could be wrong. It could be very close, and you could have dust in the system that makes it red, and so it's not actually redshifted, but it's just close by, but dust obscured. And so there were a lot of groups finding those redshift 15 galaxies photometrically, but then really to confirm them with the spectra, so where the lines are, you can directly compute the redshift, and so the distance So that has been new. Yeah, so it is about finding them, but then, as you say, I mean, we didn't know anything about the chemical properties of those galaxies, right? And this is really what's new. And even with the model, we didn't know the metallicity from models. We kind of, okay, they have to be lower metals, right? Less metals because metals grow over time, right? And then what we find was kind of interesting that actually some of them are not metal poor at all, right? As we expected.
Right. Yeah. That we're seeing the presence of, say, oxygen in galaxies that are still just a couple of 100 million years after the Big Bang. And you would need to have gone through the hearts of stars, this nucleosynthesis process, to get that oxygen. So let's shift into that second part, I guess, of the question is the new stuff. What is when you are now sort of thinking back on what you've seen over the last few years, what has just felt genuinely fresh and new and really surprising?
Yeah, there are a couple of things. So one thing is, for example, thanks to the resolution of JWST, we could actually resolve galaxies on several thousand light years for the first time. So we could measure the structure, evolution, and we know from cosmological simulations that galaxies, they start very turbulent and then they build up their disk structure over time, about, like we thought, a few billion years. So one new thing was that we found with JWST, this rotating disk, kind of disk galaxies in the early universe, right? So that means that the structure formation of the galaxies themselves is quite much faster than we thought. So that's on the structural side. And then on the chemical side, and then also in terms of mass. So similarly, galaxies, they grow in the mass of the stars, so the stellar mass over time. We found some that are very massive. And that's basically, again, because JWST's wavelength coverage is very different. So it's more red than what we had before. So we can find those more massive and also dust-obscured galaxies in the early universe. And so that's then brings me to the chemical evolution, right? So we found that some of them are very dust-rich, which means very red. And then with spectroscopy, we could also show that most of them are already very enriched in metals, which meaning oxygen, carbon, iron, much earlier than we thought.
And I mean, there is this sort of weird, I mean, there's been this open question about that early formation of these large galaxies. I think, our traditional sense is, say, like a grand spiral galaxy like the Milky Way or Andromeda or whatever. They are the result of dwarf galaxies coming together like building blocks to make these larger galaxies. But is that, when you look at, say, the Gaia data, we're seeing, say, the various mergers, the Gaia Enceladus sausage, the Kraken merger at like 11 billion years ago, and that there's still a cloud of dwarf galaxies around us. Is that sort of model holding up, or does it feel like there's something else that is just sort of these giant spirals are just forming in place day one?
Yeah, it's a very good question. So, well, one thing how you can make those spirals early is if you have a lot of mass, right? That kind of stabilizes the structure, right? So that ties a bit in what I said before, that some of them are quite massive, and forming those structures already. But yeah, I mean, it's a big range, right? I mean, we still see very like tiny low mass galaxies, and what people then have tried to understand is the overall structure formation of the universe. So how does it tie into lambda CDM, which is kind of the standard cosmological model? So you can predict how many massive galaxies you would have in a given time, right? And how many dwarf galaxies you have in a given time. There were some, in the early times, there were some claims that lambda CDM is broken.
Right. I was going to ask you that. So yeah, by all means, tell me, how's lambda CDM doing?
Yeah, it's doing well, I would say. Yeah. So the main issue still was that to measure a stellar mass of a galaxy is actually pretty hard at these redshifts. And the problem is that you need to observe the older stars which make up the mass of the galaxy. And to observe older stars, you need to observe the infrared light, right? And now if you are at redshift 13, your infrared light is actually shifted still out of the JWST coverage, even for JWST, right? And so it's really hard to actually measure the stellar masses of those galaxies.
Is it in far infrared, or is it all the way to microwave? Like, can you bring ALMA online, or do we need a far infrared space telescope?
Exactly. You need something in between JWST and ALMA.
Right.
So the JWST has two instruments, right? So there's NIRCam, which covers up to 5 micron, and then MIRI, which covers beyond to 30 micron. So to really measure stellar masses, you need to be in the MIRI regime, but MIRI is not very sensitive compared to NIRCam, right? And so that's an issue. For massive galaxies, you can use it, but you still that there's a bit of a sensitivity limit there in the end, right?
And so, like, was this always anticipated? That, because I know that, like, during a previous decadal survey, NASA was, or astronomers were proposing the Origins Space Telescope, which was going to be sort of like a bigger version of Webb with a far infrared capability that would give you that, insights into that epoch.
Mm-hmm.
Was it always sort of anticipated that we knew that we would have this problem? We wouldn't really see those building blocks coming together?
In a sense, yes. Yeah. I mean, JWST was made at this high redshift to really just find the galaxy spectroscopically, right? Which there was a lot of success. But even for example, to measure the oxygen content of a galaxy, which means the metallicity, right? You need some certain emission lines that are distributed from 3,000 angstrom, so 300 nanometers to about 700 nanometers. And so even at very high redshifts, speaking of redshift 10 now, right? Those lines, they are not covered. All of them, not all of them are covered by JWST, which means it limits our measurements of the metallicity of those galaxies. So they're still, we know that they are there, the galaxies, they're confirmed, but to go even one step further and measure the chemical evolution at really the first time, right, where galaxies are forming, I think we need look forward to another telescope that covers that regime, right?
And the next big mega telescope that's going to be coming online will be like probably the square kilometer array that could sort of observe into that regime. And like the big ground-based telescopes, they don't stand a chance. But then you're way off on the radio, and now you're too far again.
Exactly, yeah. Which gets you another interesting thing, which is the gas content of the galaxies, right? Which is currently ALMA is the workhorse in getting measuring the gas content, right, of galaxies, which is very important because gas is where stars are being formed, right? Cool gas. And so with this new radio sub-millimeter instruments like NGBLA or SK, that's going to be really interesting. Because that really gives you, for example, a time scale of star formation, right? So basically, how much gas do you have? How much stars do you form, right? That tells you how much gas it's going to be consumed per time, right? And that tells you a lot about the formation of those galaxies.
So that's sort of the formation story, which, more information needed, I guess. What about the role that the supermassive black holes are playing in the active galactic nuclei that we see? Yeah,
this is still an unresolved question, right? I mean, the problem here is that, okay, so we have JWST, we can measure the black hole masses, and we do this by looking at emission lines like hydrogen alpha, that it's broadened by the thermal kinematics of the gas, right? And that tells you that there's some kind of accretion in the center of those galaxies, which we call active galactic nuclei, which basically means a supermassive black hole that's accreting a lot of gas very quickly. And we found that for some of the galaxy populations that we found at JWST, this supermassive black hole is overmassive. So you would expect kind of a relation between the total mass of the galaxy versus the black hole mass because they're kind of co-evolve, right? That's at least the model that we have now. So some of them are more massive than what we thought. It could also be that it's really hard to measure, like a few tens of miles little dot the mass of a little dot in a gigantic galaxy, 13 billion years ago. So there's a lot of uncertainty on the masses of those black holes. But generally, what we haven't found so far is lower mass black holes. And so you have to form those massive black holes, and there are a few formation scenarios. So you can have a direct collapse, so you have a gigantic star, and you collapse the whole thing, and you get a black hole, a pretty massive black hole seed, right? That then grows to the black holes that we find. So, but we haven't found those intermediate black holes, kind of, or small first baby black holes, kind of, right? That formed and the massive black holes that we see. So that's still an unresolved question.
And I mean, we still have this several possible mechanisms. You've got that you get regular stars like the sun, or maybe 25 times the mass of the sun, die as a supernova, generate a stellar mass black hole. They find partners, those partners find other partners, and you slowly merge your way up, all the while continue to feast on the material that is in your surroundings. And then that's sort of the one pathway. And then this other pathway is that maybe these things can be 10,000 times the mass of the sun and just directly collapse, or maybe even just clouds of gas can directly collapse and get you a black hole. Are we making any progress on knowing which one of those pathways seems to be more likely?
Yeah. So there's this it's not new, it's like 30 years old, but idea of those very supermassive stars, right? So these are stars that are 1,000 times the mass of the sun. And so you can only build them in the early universe where you have mostly hydrogen, right? And they're very short-lived, a few million years. And they could potentially grow to those seeds, right, that you're talking about. And there is, you probably know about the little red dots that have been found, right?
Yeah, I wanted to bring those up so we can just go straight into that.
So this is an interesting connection because those little red dots are super compact galaxies with a supermassive black hole in the middle that's accreting. Some of them have broad hydrogen alpha lines, which tells you that there is actually a supermassive black hole in the middle. But it's still, we don't really know what they are, honestly. But those supermassive stars, they could be one of those, let's say, progenitors of those little red dots.
I mean, if I understand, like these little red dots, they are, they're glowing in the infrared. They seem very compact, like like the mass of a galaxy compacted down into something that's more like a globular cluster. Like it's a very compact object out there.
Correct. Yeah. So they're unresolved with JWST, right? So they are what we call point sources, and you get a limit on the size, right? And it's a few tens to 100 of parsec, which is 300s of light years, something like this, right? So it's really, really compact. And to stuff so much matter in there, right? I mean, they're 10 to the 8, so 100 million solar masses in mass, right? So you have to put this in this very compact objects, right? And to have them just and so the problem is if you have star formation on such a compact region, you kind of blow apart the whole thing, right? So there must be some kind of, we don't kind of understand how you form those sources. Yeah.
It's really funny to me to watch. So as an outsider, as a journalist, as I'm reporting on this, it really feels to me like these things are more exciting than the astronomers are sort of allowing their emotions to let them sort of see, because as you said, you've got this thing that has 100 million times the mass of the sun, and it is compressed into an area that is, as you say, 30 to 300 light years across. Like this is the size of a globular cluster. This is a very small-ish object, or even smaller, right? And yet it has got this amount of mass that is collected into this area. And yet we don't see these things evolving into other objects later on in the evolution of the universe. Like there should be this really clear, like there's the red dots seen in James Webb, and there they are seen in Hubble 2 billion years after the Big Bang, and here they are in their modern day. We don't see that connection. So it's like they're changing form at some point.
Yeah, this is exactly the interesting thing, right? Why are they only visible at these early times, right? Why haven't we found them today, right? There is a recent paper actually by Lin et al. Who find at least 3 of them in the SDSS, so in the Sloan Digital Sky Survey, at very local redshifts. The question is, are those the same objects than 13 billion years ago? We don't know, but at least they show very similar signatures. So they're very, very compact. They show an accreting black hole in the middle. They're, by the way, also unresolved. So, right. There are indications that when you look at them in Hubble, because they're closer, right, you see some kind of tidal structure to it. So there might be some merger gas inflow scenario, right? Because that thing has to be fed, right? So you have to throw gas on it. So the gas has to come from somewhere, right? So you have to accrete it. It's very interesting that similar objects has been found, well, 3 of them, right, in millions, right, in at lower in the later universe. But yeah, that's really it maybe seemed to be kind of a short-lived phase, right, in the galaxy evolution of those particular objects, and they eventually merge. There have been some reports of dual little red dots. So they're literally like 2 probably merging in some time, right? So yeah, it's a very interesting subject.
So what advances do you think, like what should people be watching for the next couple of years as the next time is spent, the phase 5 in James Webb goes through, you get more and more observations. What are some of the big mysteries that you think are going to start to fall?
I think we have some. Okay, so I think those observations so far have triggered some more careful investigations of theoretical models that we can prove, like the supermassive stars. We're working on models to include them in our simulations to actually predict what other signatures there could be, right? So I think this might be an interesting area, and there are a lot of efforts to look at galaxy clusters that lens background galaxies and magnify them. So one avenue we're trying to go is to find those first stars. So very metal pool galaxies with signatures of what we call population-free stars. So the first generation of stars, those very massive stars. So I think that's something an area where I think we make progress significantly.
I mean, I sort of think about how some of the most distant galaxies seen with Hubble before Webb were all the result of these gravitational lenses. We see a galaxy at 500 million years after the Big Bang thanks to a gravitational lens. Now Webb can just do those kinds of observations just wherever it wants to look. But then it's going to have its version of peering behind gravitational lenses. Have a lot of them been seen? Because I haven't sort of heard of a lot, or I haven't thought about a lot of papers that I've seen where people have said, oh, we're looking at this galaxy at redshift, I don't know, 12 or whatever, seen through a gravitational lens. I haven't seen a lot of this work done yet.
Yeah, that's correct. So it's really hard because think of it, the volume that you survey behind a local cluster, right? So you have the local cluster in the front, you have the background galaxies that are being lensed and magnified. That volume is tiny, right? So in order to find redshift 12 galaxies, which are anyway rare, right, you have to survey a large number of those clusters, right, to increase the volume in order to find them. And so there is a program that's doing that for about 60 clusters that's ongoing now. So I think here it's really a matter of numbers, and to really have those very lensed high redshift galaxies.
Right, because you have the lens, but you need to make sure that there is something that's in that distance range on the other side of the lens.
Yeah, it has to be perfectly aligned to get magnifications of like 50 to 100.
Oh, that'd be amazing,
right?
Yeah.
Which, by the way, a factor of 100 in magnification is the same as a factor of 100 squared in exposure time, right? So think of it as this. So if I magnify something a factor of 10, I would have to, if it's unmagnified, I would have spent 100 times more telescope time on it. Right. So this is why it's so powerful, right?
Right. It's like an instant Webb deep field in one tiny little area.
Exactly. Yeah.
Yeah. Speaking of the Webb deep field, it hasn't been begun. People, there are various separate surveys. There's the JADE survey. There's the, what's this? There's the C. Anyway, there's a bunch of these surveys that are going on. And what would you like to see from an actual proper long duration survey of some chunk of the universe?
Yeah, that's a good question. Yeah, there are several. So there are the deep surveys. Like
CERS, that's it, CERS. Yeah.
There's Cosmos Web, which is less deep but wide, right? So you need both. One thing that's quite interesting is now we are getting a bit more into what's called time domain astronomy. So there are a lot of sources that are variable in time, like black holes accreting. They vary on the time scale of weeks to years, right? And so one cool thing you can do is to now survey a field at a cadence of half a year, because the JWST cycles are every year, so you're gonna have like a year cadence plus minus. You can observe each field about twice a year. So that's going to be very interesting, and to go really deep with cadence over a few years, and that opens up basically a fourth dimension, right, of time, right, time variability.
So sort of like Vera Rubining your James Webb observations. And so instead of doing one big long observation, maybe you do 2 or 3 with a 6-month time delay, and then you look and see whatever changed.
Correct. Yeah. And that's also really getting into a lot of cool science now, because now you can try to find supernova explosions in the early universe. You can count how many stars explode, right? From the light curve and the spectrum, what kind of star exploded. And so with that, you can study what are the stars there, like how many, very massive stars are there in that galaxy on statistically, right? If you find those supernova explosions in different areas of the sky. And so you can start to figure out what's the mass distribution of stars in those early galaxies. And that tells you directly something about how the galaxy grows, right? Does it grow more massive stars than low mass stars, or vice versa? Obviously, our models tell us that there will be more massive stars in the high redshift universe, because you have those a lot of hydrogen gas that makes up those massive stars, right?
Yeah, that's really interesting. All right, well, I'd like to shift gears and chat a bit about dust. Because that is a bit of a meme here on the channel, that dust is the enemy of astronomers everywhere. When you think about a lot of the major announcements that ended up to be wrong, dust was often a culprit.
Yeah.
But we were talking before this interview, and you're like, in fact, the sort of the metallicity of the dust changes over time. That whole process of nucleosynthesis is sort of a part of the dust story as well. So give me a sense of how dust has been changing over time throughout the age of the cosmos.
Yeah, so that's very interesting. So there are a couple of mechanisms how you can form dust, right? So speaking about supernova, so whenever the supernova goes off, it basically produces a bunch of dust, right? You can also form dust in a life cycle of stars, just by over billions of years. These are more lower mass stars, because low mass stars, they live a longer time, right? So you have dust production over an extended period of time. Then you can also form dust in the galaxy itself by smaller dust sticking together, just growing. Like in your bedroom, when you don't clean for a while, you get those dust.
Dust bunnies, dust
bunnies.
dragons.
Yeah, they grow over time, right? If you don't vacuum a while. Same thing, just smaller scale, right? I mean, we're talking here about micrometer scale, right? It's not the dust that you can see by eye. But I mean, eventually it makes up our planets and ourselves, right? So it's a really interesting field to study. And so what we think in the early times is that you form. So what we found with JWST and also with ALMA is that those early galaxies are quite dusty. And so we're speaking about, 400 million years where you have to form this dust, or even less, right? If you're redshift 10, it's even less, like 300 million years. So how do you form the dust so quickly? Well, again, you have those massive stars in the early universe that go supernova pretty quickly, and they produce the first dust of those galaxies. And that happens really quickly on 100 million years. So we think that the first dust forms via those channels. And then as time goes on, you have just through stellar processes, you form more dust. And you eventually also have a shattering mechanism where you basically shatter large dust grains into smaller ones. So current models, they show that you first actually form large dust grains. And the smaller dust actually is produced by shattering later on. And so the dust population changes of large grains to small grains as cosmic time evolves, right? And then, eventually you have in the cool areas where dust then will grow to more larger dust grains that then eventually form planets, right? And
so, this whole process of dust accreting together, sticking together, maybe electrostatically, and then finding larger until eventually gravity can be the force that's starting to take over. Does that put any limit on when planets might be able to form around stars?
That's a great question. Yeah. In principle, yes, you can predict when the first planets will form. I believe there was a while ago, I don't remember the authors, but there was a paper saying, you can form planets actually very early on in the history of the universe, right? So that's an interesting conclusion from that. Yeah.
And so does, when you're looking back to the earliest times in the universe, we're talking about these little red dots, or even these active galactic nuclei, where you've got this black hole that is surrounded by this dust. Is it primitive dust, right? Where it absorbs different wavelengths than compared to maybe the stuff that you might see around a active galactic nuclei somewhere relatively nearby?
Yeah, exactly. So basically the dust grain size dictates what wavelengths it's going to be absorbing, right? And so you have another thing in this so the environment at very early times is very dynamic and very harsh, right? Through the radiation of the super young stars, they ionize basically the whole medium around them, and then you have the accreting black holes. So it's very turbulent and messy, right? You can think of it, and so and that also impacts the dust, right? And so in those very early times, you have pretty primitive dust that's formed there, right? Yeah, and it's very different to what we observe now, actually.
And what is your relationship with dust? Do you do you find it interesting, or do you wish it would all go away?
So there is a say that we say in the astronomy community. So first, in early career, you avoid dust, right? Because it's just gives you problems, right? You think the redshift 8 galaxies are at redshift 2, right? So, and then vice versa. It's very complicated. And as you go further in your career, you start getting interested in dust. And so I'm at this point now. So it's not as annoying anymore. It's actually a really cool thing. And really what excites me is that we haven't really been able to see a probe dust in the early universe other than through absorption. So we see light from the UV. We expect this much. It's not there. So we have absorption, right, of some kind of dust. The exciting thing now is that with JWST, we can actually look at the dust grains themselves, right? So each dust grain or mode of dust molecules, right, it emits light at a specific wavelengths, causing what we call emission lines. And we can probe those with JWST now in the early times. So we can actually not only see dust in absorption, right? So dust is there, but we can actually probe the properties of the dust. And that's really exciting now. And in fact, the MIRI instrument on JWST was basically made to look and characterize the dust at early times.
Yeah, it's funny. I liken it a bit to like an archaeologist who's looking through a garbage dump.
Yeah.
Right. Yeah. That they're looking at what is being processed by the culture as a way to better understand what the culture was like. The dust is the output of these stars, these galaxies, these supermassive black holes, and they tell you how busy these places were back in the day. Andreas, what are you obsessed with right now?
Other than dust.
Sure. Yeah.
Yeah. So
did I steal your obsession to talk about dust?
Yeah, that's not my obsession. Yeah. No, there are other things too. I'm very obsessed about, well, obviously dust and metal enrichment in the early times. And I'm obsessed about new models, how we can tie those observations to our current simulations. I'm also obsessed about something that just comes to my mind is new space telescopes, right? So there's the SphereX infrared telescope that has been launched in March last year. And it's surveying the whole sky. And so that gives us, and obviously it also covers dust, right?
Right.
And that's really exciting.
I mean, it's a really fascinating instrument because it is able to essentially observe whatever 100 different wavelengths of infrared radiation kind of at the same time. It's like slowly changing the wavelength, tuning it as it's making its observations. And you're not just getting, oh, we just want this specific wavelength. We're just getting the whole package. And that's never been done before.
Exactly. Yeah. This is totally new. And it's a very interesting design. It's a very simple telescope. But it works beautifully, and it gives a lot of science in the Milky Way, but also in local galaxies and a bit farther away. It's not going to see the very high redshift universe, right? So, but it's also very interesting or important to understand the local universe very well. And we still have different environments, like in local galaxies, that are resembling the earliest environments that in the early universe, right? But they're much closer, right? So we have more data and we have more resolution. And so it's very important to study those local environments very well and understand them in order to predict and explain what we see at high redshifts.
I mean, it really is a fascinating time when you think about all the tools that we have at our disposal at this point. James Webb, which you've been working on, SphereX even, which I'm sure a lot of people aren't even that familiar with, upcoming Nancy Grace Roman, the Vera Rubin that's coming online, the Euclid mission, the DESI survey, work that the Chinese are doing. Like, it's kind of amazing how many tools are all out there available trying to answer these same questions. And I think they've just been such what is dark matter? What is dark energy? What is the evolution of the universe? They've been around. These questions have been around for so long that finally the cavalry has shown up to bring the tools, to put them into the hands of the astronomers to try to give us some answers.
Exactly. Yeah. And the new thing now is those wide field all sky survey. I mean, SphereX is all sky. Euclid is probing a large chunk of the sky, Roman as well. And so we can now connect, and that's actually something I'm also obsessed about. So you can connect now the very small scales, right? JWST, hundreds of light years, very compact objects, resolution, of the star-forming clumps and so in galaxies. But then also combine this with the wide field, right, where you can measure the really like the backbone of the universe, right? So all the cosmic structure and the filaments that feed the most massive structures in the universe, so the galaxy clusters that I mentioned before for the lensing, right? They have to be fed through filaments of flowing in gas, and so that's kind of a new angle now, um, and it's very perpendicular to what JWST does, but we need both sides to understand galaxy evolution, right?
Right. Yeah. Well, Andreas, thank you so much for taking the time to chat and give us the modern cutting edge update on what's happening with Webb and this search into the earliest part of the universe.
Yeah. Thank you for having me.
I hope you enjoyed this interview with Dr. Andreas Feist. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Barry Lee Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailock, Cy Nelson, Dark Finga, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Roebuck, Rank Heidi, Richard Williams, Sean Sargent, Stephen Fowler-Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldebor Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. This is great. I've been wanting to do an episode like this for a little while, and I was just looking for the right target, the right victim. Someone who is working with cutting edge James Webb information, is really thinking about these controversies, these new discoveries, sort of turning what was the theories about the early universe and finding out the practical realities. And like, I find information moves very slowly in this field. People are still wondering what the great attractor is. People are wondering about what quasars are, and yet, you're staying up to date. Just how quickly this field is changing and how these new tools are giving us this golden age in astronomy. What were mysteries before are slowly, one by one, revealing their secrets. And again, we've only had a couple of years with this magnificent telescope, and we still have, hopefully, more than a decade to continue to unravel all of these mysteries. So I hope you enjoyed this conversation. Now you are totally up to date with what's happening with James Webb, and I'm sure we're going to have to do this again, probably once a year with different researchers to stay on top of it together. All right, we'll see you next time.